The second problem we're going to do here is a work problem. So we see that we have a barrel of water is in the shape of a cylinder. So first I'm always going to draw this. So here's our barrel of water. It's in the shape of a cylinder with radius 0.5 meters. So this is R equals 0.5 meters. And we have a depth, which I'm going to call H, is equal to 2 meters. And we're given that it's half full of water. So if this is our boundary here, we're given that actually everything in here is full of water halfway up. So halfway up is, of course, 1 meter. Okay. We want to find the work required to pump out the water from the top. So what we're going to do is we're going to take a small chunk here, a small little chunk, assume this chunk is really small, it has width or height dy, and we're going to move this chunk out of the water. Now we're going to do this for each chunk, a bunch of really small chunks, and move them out together, and we're going to do that in an integral. So let's see what this chunk looks like. If we just draw it over here, now this is a little chunk of water, right? Now, what we need to do is we want to find dV. So this thing still has radius r is equal to 0.5 meters, and it has height dy. Okay, so we know that the area, or the volume of a cylinder, is given by pi r squared, which is the area of the circle, times the height of the cylinder, pi r squared dy. So in this case, it's going to be pi over 4 dy, but I'm going to keep working with the r squared because it's easier. Now if you're interested, you can check, is this really a volume? Do the units work out? Well, r is in the radius r is in meters, so we have meters squared, and dy is a height, so this thing is also in meters, so times meters, and we have meters cubed, and it checks out. Volume is in meters cubed. Okay, so now, because work is equal to force times distance, we want to figure out the force, which is why we found the volume. So now that we have the volume, we need to find the mass, because force is equal to mass times the acceleration, and then we have this distance in here. So now we're trying to find mass. So once we have the volume, we just multiply the volume by the density. So we know that dm is equal to rho dV. And I call this dV because I'm saying this is a very small chunk, and we're going to integrate it at the end. So this dm is also a small chunk, and it's the mass of the small chunk. So we see above that rho is equal to 1,000 kilograms per meter cubed, which I'm not going to plug in yet. I'm just going to write this as rho pi r squared dy. And if you want to check units, well, rho is in kilograms per meter cubed. Kilograms per meter cubed. Oops. Times meters cubed. So it's kilograms, which is mass, so it checks out. Good. Okay, so now that we have dm, we want to find dF, because now we have the mass, we want to find the force. Now, dF, so that's the force that this little chunk exerts, is just gravity times dm. You can think about this as a weight, so often this is used as a pound. So here we have rho g pi r squared dy. So now this is our force, and what we really want is work. So to find work, we need to figure out how far we're going to move this little chunk up. So this d in the distance is this d, how far it needs to go so that it's out. Okay, of the water. So let's see what we can do about that. Let's go ahead and draw another picture over here. So this is our barrel of water. We have a chunk over this that we want to move out. Now let's say that this chunk is at some height y. If we set the y-axis to be 0 here. So the chunk is at some height y, and we want to essentially say, how far is this? So how much do we need to move this little chunk if it's at height y? And because this up here is y is equal to 2 meters, we know that this distance has to be equal to 2 minus y. Now we can check this. I'm going to use my yellow pen for checking. We should have the distance at y equals 0 should be 2. When we're at y equals 0, we should have to move it 2 up. Distance of y equals 0 is equal to 2. That works. And then we should have the distance when y is equal to 2 at the top. We shouldn't have to move that up at all, right? That should already be up there. So we have distance of y equals 2 is equal to 0. That also checks out. Okay, so we're good. This is the right distance function. Now, what we can do is we can write dw, which is the work required to move this small chunk out, is going to be distance times df. So we just set our distance function here as 2 minus y. And then if you recall, if we look back at what df is, it's rho g pi r squared times dy. Rho g pi r squared dy. Good. So now, in order to get the work, we just need to integrate it. We write work is equal to integral dw. Now, but we need to figure out what the bounds are. This can be a little bit tricky. We're told that the water is goes halfway. So that means we need to integrate, well, certainly we're going to have water down here, and then the max water is going to be up here when the height is equal to 1. So that means y ranges from 0 to 1, because we only have water up to y is equal to 1. So this integral, well, we look at dw, and everything's in terms of y, so it should be, we have 2 minus y, rho g pi r squared dy, and our bounds are going to go here, so we go from 0 to 1. And remember, these bounds should always match this. Okay, so now we can just integrate these things. These are all constant, rho g pi r squared. So let's bring them out. And we have rho g pi r squared, integral from 0 to 1, 2 minus y dy, which we can integrate pretty easily. r squared, and we have 2y minus 1/2 y squared from 0 to 1, which is rho g pi r squared. 2 minus 1/2, and the other terms are 0. So this is 3/2, so we have 3/2 rho g pi r squared. Now we're going to want to write this all in terms of actual numbers, so at the end we have work is equal to, what was it, 3/2 rho g pi r squared, which is 3/2 times 1,000. Let's see if we can write that better. 1,000 with the density. Gravity is 9.8 pi, and then our radius was times 1/4. So this will be our final answer, and you could simplify it if you like, but that's fine.